Okay, so we left off last time at optimal page replacement. So talking about what we do whenever we run out of physical memory and we need to put something new into physical memory. So we have a request for a page that we're going to access. We want to make sure that we can actually put that page into physical memory. We need to figure out which one to do that with, or which page to replace. And so optimal page replacement is that we replace the page that will not be used for the longest period of time. So that is provably the best policy that we can possibly use. However, it's difficult to implement in practice because we have to have an oracle that knows which page will not be used for the longest period of time. So in practice, we have to try to approximate that some way because it's very difficult to actually know which one is going to be used furthest in the future. So what we're going to talk about today are a bunch of policies that attempt to approximate this optimal page replacement policy, but do so in a way that they don't actually get to the optimal, but they're close. So first off, we're going to talk about LRU, which is least recently used page replacement. So this is sort of the standard bread and butter way to approximate the optimal page replacement policy. We just look at which page has been used least recently, so which one was used furthest in the past, and then we replace that. So it's kind of similar to the FIFO policy. FIFO was kind of the same policy here, where we would look at the thing that was put into memory longest ago, but here we sort of change the policy a bit in that if something was put into memory a long time ago but keeps getting used recently in the past, now we won't replace that. So it doesn't have this sort of inevitability that the queue had, where the queue would eventually replace everything. Least recently used will continue to replace the thing that has been used furthest in the past, rather than the thing that was brought into memory furthest in the past. So we have to, for least recently used, we have to keep some measure of when, or like which thing was least recently used. So we have to track this in some way. We can do this either with a timer, or maybe with a queue or a stack, just some sort of data structure that we can put things in and then move them around whenever they get used. For now, I'm just going to use a timer here. So we have the same string of entries that we would have had previously. We're just going to start at time. 0 is here, and then time, n is here. What do we have? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So up to time 11. So we're just going to basically, every time we access a piece of memory, we'll increment the count. So page 1 is accessed at time 0 when it's brought into memory. Page 2 is accessed at time 1. Page 3 is accessed at time 2. Now we get to, with our 3 frames, page 4. Page 4 is not in memory, so that's going to be a page fault. We have to decide which of these things are we going to replace. And so here it's a pretty easy choice that we have page 1 that is put in at time 0. So clearly that's the choice to replace. It is the least recently used thing in memory. So we're going to put 4 in place of page 1. We're going to cross out the time, and page 4 was brought into memory at time 3, or was most recently used at time 3. So now we continue. We're going to again have a fault on page 1. We're going to bring it in place of page 2. So that's the least recently used thing since it's 1, 2, 3. We'll replace that time. Now it was used at time 4. And we continue on from there. So I got you started here, but I would like you to then basically finish this in your groups. So go ahead and take a couple minutes and finish walking through this with least recently used. And then we'll come back together and finish it up. So go ahead and split up. Be back in a couple minutes.
Hello. Where is Gary Kasparov? I don't know.
Okay, so let's continue through this, and then I had a question from Kira about how this is better than FIFO. So we're going to do a slight extension to this just to demonstrate. So we should have then that when we access 2, that's a fault because 2 is not in memory. We're going to replace 3, and we'll update the time to 5 here. It's going to get a little messy here. 5 is not in memory, so that's a fault. We're going to replace the oldest thing, which is 4. So we'll have 5 here times 6. 1 is now in memory, so that's not a fault. Not a fault for 2 since 2 is in memory. 3 is not in memory, so we have to replace the oldest thing, which is now 1. So 3 is going to go in there at time 9, I believe, is where we're at this point. 4 is a fault because it's not in memory. We're going to replace 2 because that's the oldest thing, time 10. And then 5 is not in memory anymore, so we're going to have another fault, which is going to go, sorry, it's 5? No, 5 is not in memory. Sorry, one of these should have been replaced, should have replaced 5. Am I wrong here? Backtrack.
I think 5 should have been replaced by 3.
5 should have been replaced by 3. So
Yeah,
this is,
you replace 1 with 1 and then 2 with 2. Then you'll replace 5 with 3.
oh, did I put the wrong thing in here? Or no, I didn't. So 6, yeah, so 5 was at times 6. Oh, right, I didn't update the times. That's the problem. Yeah, so 1 was accessed at 7, 2 was accessed at 8. Sorry about that. So then 3 ends up replacing the 5, and that's our third fault there. At time 9, 4 ends up replacing 1 at time 10, and 5 ends up replacing 2 at time 11. And that gives us our 10 faults. This is the worst thing that we've looked at so far for 3 frames, right? We looked at, you know, the optimal page replacement. So what we want to get to is 7. With 3 frames, FIFO is actually 9. So this is worse than that, which makes us wonder, why would we ever want to use something that's worse than this? So let's look at this. If instead we have 4 frames to use. So we have page on the left, we have time on the right, and we're going to have 4 of these frames to put things in. So same pattern here. We're going to go 1, 2, 3, 4 for our cold misses. And we have time 0, 1, 2, 3 that these happen at. Now we're going to access 1 and 2. They are still in memory because of the fact that this is, you know, this is a 4-frame table now. So we have room for those. So we're just going to update their times to 4 and 5 because they were accessed, but they don't end up having faults. We then access 5. And 5 is going to replace 3 because 3 is now the oldest thing, or the least recently used thing in the table. So that's going to be brought in at time 6. That's our 5th fault. We access 1 and 2 again. So 1 and 2 are again going to get updated, but not removed. So now they get updated to 7 and 8 time, but there are no faults. We then access 3, which is not in memory. We're going to replace the oldest thing, which happens to be 4. At time 9, so that's a fault again. And then we're going to replace 5 with 4, and that's going to be at time 10. That's another fault. And then we're going to replace 1 with 5 at time 11 because that's the oldest thing. So the benefit of LRU is that it is an approximation of optimal without having the Belides anomaly side effect of the FIFO Q solution. So this will not have the Belides anomaly effect of, as we increase the number of frames available, ending up with a worse number of faults due to the way that the Q works in FIFO. So it's still not optimal for sure, but it is sort of the best way of approximating optimality, or one of the best ways of approximating optimality without without actually having the optimal policy. And again, the key here is that as we increase the number of frames, the number of faults should go down. It shouldn't ever increase. So as we add more and more memory to a system, or as we decrease the page size if we want to have more frames available, we can end up with less faults occurring because of the fact that we can keep more unique things in memory. Okay. Any questions on that? Okay, so I'm going to add this to the notes. So increasing available frames. Oops, available. Okay, so we don't suffer from Belides here whenever we increase the number of frames. So there are two ways we can implement this sort of a process, right? We can have a time that is an integer, and that integer can basically be increased every time we make an access to memory, so that we have a sort of unique counter of how long ago something was accessed. Just for the class, we don't have to talk about this, but what might be a problem with using an integer to track this?
It's fixed sized.
It's fixed size. So what can happen with a fixed size integer?
Overflow.
Mm-hmm. Right. So at some point we go from 4 billion, 200 million, etc. We go from a very big number back down to 0 as we increment. And so this is a problem because now all of these things that were accessed at 4 billion something have a very high count, and 0 has a very low count. So now the thing that we most recently accessed will look like it is the least recently accessed thing in memory. So we probably need to do some sort of counting where we kind of figure out how long it's going to take for things to get removed from memory, and maybe have sort of like a counter plus a version of the counter, so that we know we basically have to have a larger counter essentially, so that we can keep track of is this a very large number that was in the previous iteration of the counter, or is this a very small number that is in the new version of the counter? And the very small number in the new version of the counter would be more recently accessed than the other version. So we might have time and a single bit for version, and we'd have version 0 for all of these. But if our counter overflowed, then we would switch to version 1 and then switch back to version 0 and just sort of toggle between those two to give us a little bit more information. We just basically want to make sure that we have a long enough epoch so that things get to the point that anything that would be reused would get reused or replaced by the time we would switch to the other version again. So if we switched back to 0, we would want everything to have been updated to version 1 by that point. So this can sort of extend the lifetime of our counter, make it a little more feasible to do this sort of an approach. Otherwise, we have this issue of the fact that the counter can overflow back to 0. We can also have a stack. So we can maintain a list of recently used pages on a stack, and basically on each access to a page, we just move the page from the bottom of the stack to the top of the stack. So it's a little more of a list than a stack. And that leaves the recently used pages at the bottom of the stack meaning that all we have to do when we want to replace a page is look at the bottom of the stack, pull that page off of the bottom of the stack, and remove it from physical memory. And again, I want to add that this does not suffer from bellities. So quick math problem to work out. So if we have a 32-bit counter that we want to add to the system, we have a 32-bit address space and 4 kilobyte pages. Assuming a single level page table, how much space overhead does that add to the system? So go ahead and jump into your groups again and take a couple minutes to work this out. Okay, so I think most groups are there at this point. So right now we're just looking at how much overall space overhead, is this, not this sort of proportional overhead. Though we can calculate that as well. So right now we just have a 32-bit counter times we have a 32-bit address space, and we have 4 kilobyte pages. So 4 KB is 4096 is 2 to the 12th. So we have 12 bits for the page offset, which means we have 20 bits for the page number. So then we just do 20 times or 2 to the 20th, and that should be equal to 4 megabytes of space. So this is non-negligible, right? We have a 4 megabyte addition to our system that's probably going into hardware, at least. So at least 4 megabytes of additional space that we need to cram onto a DRAM chip or somewhere in the hardware to keep track of this counter so that we know how often a page or a frame has been accessed. So implementing LRU is sort of non-trivial as well. It's not as non-trivial as optimal page replacement maybe, but it is still going to have some significant overhead. Now in terms of the proportional overhead, if we have a 32-bit system, we have 2 to the 32 worth of memory to use, equals 4 gigabytes. So now we have, instead of 4 gigabytes, we, in terms of the proportional overhead, we would have 4 gigabytes, we'd have 4 gigabytes plus 4 megabytes divided by 4 gigabytes. And that would give us our sort of like, this is the amount of overhead that we have over our, previous system without a counter. So we'd have, 4 times 2 to the 30th divided by 4 times, or just 2 to the, 4 times 2 to the 30th plus 4 times 2 to the 20th plus 4 times 2 to the 20th divided by 4 times 2 to the 30th. And that would give us our actual proportional overhead, which is very small, right? It's 1.000977 if we round. So this is not a large percentage overhead here. It's less than 1%. So less than 1% overhead. But it is still a significant amount in terms of the physical memory that we're adding in. So maybe not that much to add into DRAM, but it is a pretty decent overhead in terms of the actual space that's being used up for these counters. Okay. Any questions on LRU so far? Okay, cool. Because LRU has substantial space and hardware requirements to do true LRU, not many systems will choose to actually provide this space in hardware to do LRU. So we've sort of looked for things that can approximate LRU. So we're already approximating the optimal page replacement policy. Now we're going to approximate the approximation and use LRU approximation instead. So we might have instead of a true LRU system, we might have this page table where instead of having page and a full 32-bit counter, we might have a bit here that tells us whether this page has been used since the bits were reset. So we could have 1, 2, and 3 were all used recently when we brought them into memory. At some point we reset these bits to 0, and then we look for things that have a 0 bit instead of a 1 bit to replace. If we can't find anything with a 0 bit, then we just replace something with a 1 bit, and we probably use something like FIFO to do that. So this can, approximate the LRU algorithm that we just saw, but it's not going to be quite perfect. Instead of zeroing out the bits, we can have 2 bits. So we can have, 1 1, 1 0 1 0. Instead, basically shift to the left by 1 each epoch. So however often we want to track the counters, we would just shift all of these bits over to the left. And then shift all of these bits to the right by 1, and then update the most significant bit each time. And so that way the counter sort of decays over time, becomes smaller, since as we shift a bit, from, if we have 1 0 0 0, if we shift that over to 0 1 0 0, that's going to be a smaller number. So we can basically, rank these on the larger the number, the more recently that was accessed, or vice versa if we want to do it the other way around. But either way, we want to have some sort of decay where the numbers shift over time. And so things that were more recently accessed will have either larger or smaller numbers. Things that were least recently accessed will have either larger or smaller numbers, depending on which way we want to orient things. But this can allow us to use significantly less bits. So if we work the same problem again, I won't have you go into rooms again this time, since we just did this calculation. But if we have an 8-bit counter now, if we have 8 bits times 2 to the 20th entries, now we should have significantly less space overhead because of the fact we're going to divide out the bytes. So this should just be 1 megabyte of space. So we can reduce our overheads by 4x if we use this sort of 8-bit counter approximation. This also doesn't suffer from overflow if we do it this way. So if we sort of, have a single bit that we always update and then shift each time, this doesn't have the issue of overflow, because we're never like directly incrementing some global counter that's going to go past its max value. We're just updating these each time they are accessed within a certain epoch. Now, again, this isn't a... Sorry, go ahead.
Sorry, I was just having a question. So, like, as far as the amount of data that's stored, it's less, but wouldn't implementing such a device in hardware, like, take up a lot more die space? Because you're looking at like potentially like a flip-flop for each of these bits. And so it'd be more like you're building like a register essentially that can like decrease. So I'm just wondering if like hardware size, is there any consideration to the balance of the physical space it takes on a die to do this versus the amount of data it represents?
Yeah, for sure. And I actually don't know. I don't know the answer to that question. What would be the implementation level overhead in terms of die space? That'd be an interesting thing to look up and figure out what the actual answer is to that. But yeah, that would be something you would definitely want to consider, because if it was cheaper to just have the full 32-bit counter in terms of die area, then yeah, we would want to go with that instead of this sort of approximation system, because the counter will be generally better, or we could have a larger counter like this of some sort, rather than having this shifting system. But yeah, that's a good point, that we do have to consider what the actual implementation is at the hardware level for each of these policies as well, since this is going into hardware. So I will take a few minutes this weekend to look that up and see if I can find that answer for you, but I don't know off the top of my head. Okay, so that is LRU approximation, basically using less bits. The other way that we can approximate LRU is to do second chance replacement. So second chance replacement combines FIFO replacement with a 1-bit LRU approximation. So if we go back to our usual example here, I'm just going to make a new book over top of this. Nope. So if we have our usual setup here, with LRU approximation, we're going to have 1, 2, and 3 in memory. 1, 2, 3, 4. 1, 2, 5. So we're going to have our bit that basically says this was recently accessed, and we're going to have our queue that we had from FIFO that tells us what order things came into the system in. So the way this works is that when we get to the point that we need to find something to replace, so we need to find a replacement to replace with 4, we look at the queue, we check to see, does 1 currently have a 1 in its bit? So this would be like the used bit, maybe. And since 1 does have a 1 in that used bit, we're going to remove it from the queue, and we're going to place it at the back of the queue. We're then going to look at 2 and see does 2, and we're going to set 1's bit to 0 there. We're going to look at 2, see that its bit is also 1, so we're going to set that to 0, put it at the back of the queue. And then we're going to look at 3 and see that its bit is also non-zero, so we're going to put it at the back of the queue. And we're going to end up replacing 1 anyways here, and putting 4 into memory, replacing the used bit with 1, putting 4 at the end of the queue. But we've given 1 a second chance basically here. So if we had a scenario where, you know, at this point we go into memory, if we would try to replace, you know, 4 eventually, we see that 4 has been used recently, and we might not replace that if there is something further back in the queue that has a 0 used bit. So we essentially give everything a second chance in the queue. Rather than immediately replacing it, we try to allow it to remain in the queue as long as it has been recently used. And so this way we don't actually need like that epoch or anything. We just have that when we loop back around to through the queue, we set these to 0, and we try to find a page that does not have that used bit set. We can enhance this a little bit to track the type of use for each page. So here we can have 2 bits. They represent used and modified. So this is like the dirty bit that we already want to have for page replacement to some extent, because that lets us track whether something has been written to or not. And usually we don't want to replace things that have been written to. Those are things that, you know, tend to be things we want to keep in memory. So we have 0, 0, which is not used and not modified. So that's the first 0 again means used. The second one means modified. So 0, 0 would mean not used and not modified. So that's our best case to replace something because we know it hasn't been modified. We don't have to write it back to secondary storage. And it hasn't been used, so no one's using it recently. That means it's probably a good case to replace this. We can have 0, 1, which is not used, but it was modified. So not used recently, but was modified. So we'd rather not replace that. We'd rather replace something that was not modified because then we'd have to do a write back for the one that was modified. We don't have to do a write back for the one that was not modified. 1, 0 is used but not modified, possibly used again soon. Might be a code page or something like that. So this is sort of our third priority to replace. And then finally, used and modified. This is our worst case to replace something. We never really want to replace something that is used and modified if possible. So this is where the second chance algorithm would then flip this bit to 0. If we try to, if we have something that is 1, 1 at the beginning of the queue, we would flip it back to 0 to say, okay, it's no longer used, but it's possibly modified. So we'd still look for something that's 0, 0 first. Eventually, though, we might replace something like this if we end up flipping that used bit. So here we just basically scan the queue until we find which page has the best case for replacement. So what this improves compared to the regular second chance is just that it will replace pages or replace modified pages less frequently. And that reduces write backs to secondary storage. Okay. So that's just an extension to again trying to approximate LRU, trying to approximate the optimal page replacement policy. So finally, we have a couple counting-based algorithms that I think you read about. these maintain a counter for the number of times that a page has been accessed rather than the time at which that page was last accessed. So we still have a per page counter, but instead of sort of having this global time that we write into that counter or into that space in memory, now we have a counter that just gets incremented as we access that page. You know, so if we go back to our example here, we would just have a counter. When we access 1, 2, 3, we increment that counter. If we access 1 and 2 again, or let's say in the case that we have 4 frames, so we have 1, 2, 3, 4. We initially have a counter that says 1 for each of these. When we access 1 and 2 again, we're going to increase that counter to 2 for each of those, and then we choose to replace things based on the value of that counter in memory. So we just do a simple increment. And then we have 2 policies. One is that we can use the least frequently used thing in memory. So this is maintaining a counter of all the accesses and replacing the page with a lower number of accesses. So here we would replace either 3 or 4. So the idea behind this is that we would want to replace things that are being used less. Because that might mean that we'd have better performance. It's less likely that something being used less is going to be used in the future again. However, it doesn't necessarily mean that something that was used less is not going to be the next thing that we use. So this doesn't really approximate the optimal page replacement policy that well, but it tries. So the issue that least frequently used tends to have is that we have this system initialization problem. So we load up our OS. A lot of the code that runs to set things up to allow you to log in, all of this stuff that sort of initializes your system gets used quite a bit whenever we start the program, and then doesn't get used again pretty much forever. But because it was used frequently as the system starts up, it might have a very high use count. And that means it might not be able to remove that from memory because we have least frequently used. So these counters can sort of saturate, and then it would take something else having a larger counter to replace that from memory. So we might have a lot of sort of dead pages in memory that we don't end up using for a very long time. So on the other hand, people have proposed the most frequently used algorithm, which replaces the page with the highest count. This to me seems like sort of an academic, let's try it, but why would this ever work? So you replace the page with the highest count, so the most frequently used things in the system. This does get rid of the problem of initialization that we have with least frequently used, but it also has the issue that we're replacing the things that are being frequently used by the system, so it's likely to replace things that we do want to keep in memory. The idea behind this was that things that we have high counts for, we might be finished with, and pages with low counts we haven't used yet, so we may want to replace those, assuming that the things with low counts will be accessed soon in the future. The sort of key takeaway here is that neither of these are common due to the fact that they don't approximate the optimal page replacement algorithm that well, but they're worth mentioning just because they do show up in the literature. And people may talk about them at some point, and it might be a good solution for something else in the future, despite the fact that it was not the best solution for page replacement. Okay, so are there any questions on page replacement? Okay, so I think Monday there is a reading quiz posted. We're basically going to move on to the next topic, which is going to be file systems. So file systems, will be the sort of, next thing we look at. We have about 9 lectures left in class. I'm going to give you a comp day next week to do the exam. So Friday of next week, we won't have class. I will try to get the exam out earlier in the week, but I do want to give you at least a class period of time that you're not in lecture to be able to do that. So we'll have lecture Monday and Wednesday on file systems, and then the exam period on Friday, but I will try to have the actual online version of the exam ready for you beforehand. So if you want to work on it before that time, you can. The exam will be due on end of day on Friday. So make sure that you are aware and plan your time accordingly. Otherwise, I think we're done for the day. So I will see you on Monday. Have a good weekend.
Thank you.
Yep.
Professor, I had a quick question.
Mhm.
When could you do